Alright. So, in the first place, Newton's second law, as you have learned, net of all external forces acting on a particle, net of all external forces acting on a particle is rate of change of linear momentum associated with the particle, right? Is rate of change of linear momentum associated with the particle. Now, there are a number of forces acting on a particle, but if they vectorially add up to 0, that means if F is 0, net of all external forces acting on a particle is 0. Particle or a system of particles. What I'm saying is just not just a particle or a system of particles. Then the linear momentum of the system must be a constant, right? Now that's essentially the law of conservation of linear momentum. That's the law of conservation of linear momentum, right? Now, it's possible that the net of all external forces is not 0. Net of all external forces is not 0, but its component in a certain direction could be 0. Let's say there is a force F. In general, it's going to have 3 components: Fx, Fy, and Fz. Now, maybe F is not 0, but let's say its component in the x direction is 0. Say Fx is 0. If the net of all external forces acting in the x direction is 0, then the linear momentum in the x direction will remain preserved. This is the linear momentum in the x direction. After all, the linear momentum vector will also have x, y, and z components. Px I cap plus Py j cap plus Pz k cap. These are the linear momentum components in the 3 orthogonal directions. So in the event the net of all external forces in a given direction, call it the x direction, is 0, then the linear momentum in that direction for the particle or the system of particles will remain preserved. Right? Now, after all, what causes change in linear momentum? A force acting on a particle or a system of particles is instrumental in producing a change in linear momentum, in the sense that if a force F acts for a time dt, it produces a change in linear momentum dp. That means a change in linear momentum is produced by a force acting for a certain time. Net external unbalanced force acting for a certain time is going to produce change in linear momentum in the direction of the force. And this force acting for a short time dt is called, this F into dt is referred to as an impulse of the force. Now, sometimes we would take recourse to certain approximations, in the sense that there could be a certain force acting. In a certain direction, external force in a certain direction. But the magnitude of that force is much, much smaller compared to other forces. There could be a net unbalanced force acting on a system in a certain direction, the magnitude of this force is much smaller compared to, let's say, other forces acting on the system. Now, wherever that happens, then the impulse of that force, F into time over which it acts, can be ignored for practical consideration. Can be ignored for practical considerations. And when we do that, then if the impulse of the force is very small, because the force into delta t is small compared to the impulse of all other forces, then we can, despite the presence of the unbalanced force, we would still approximately preserve linear momentum in that. For example, there is a mid-air collision. Let's say there is a mid-air collision of two particles. There is a mid-air collision of two particles. Now, when this mid-air collision takes place, then there is an unbalanced force acting on the colliding units. The unbalanced force is the force of gravity. The force that they exert on each other by means of the impact, that's an internal force for the system, and that will cancel off in pairs. But gravity, Mother Earth, which is acting on the two particles, is unbalanced. So the period for which the colliding units interact, could be some delta t. And in this period of time, the impulse of gravity, which is mg into delta t, impulse of gravity would be mg into delta t, which is its propensity to produce change in linear momentum in the vertical direction, because mg acts in the vertical direction. So impulse in the vertical direction that gravity produces is mg into delta t, with the objective of producing change in linear momentum in that direction, is small, because that mg could be really, really small compared to the forces of impact across two colliding units. When they collide against each other, then the force of collision could be much, much larger than the force because of gravity, which is mg. And therefore, the impulse produced by gravity, mg into delta t, is so small that for all practical considerations, in a situation like this, for example, one could choose to ignore, and one could still preserve linear momentum in the vertical direction despite presence of an unbalanced gravitational force acting on the colliding units also. You know what I'm saying? Are you there with me on this? Right? So sometimes these forces, where mg kind of forces, where mg into delta t is so small that it could be ignored, these forces sometimes we would refer to as non-impulsive forces. We would refer to such forces as non-impulsive forces. Gravity, for example, we would quote unquote as a non-impulsive force. Down the line, when we look at spring systems, the spring force again would be looked upon as a non-impulsive force, and so on and so forth. Let me treat the law of conservation of linear momentum. Let's say there is a particle of mass m projected in the gravitational force field with a velocity u, making an angle 60 degrees with the positive direction of the x-axis. At the highest point, there is an internal explosion that takes place on this particle. The highest point, there is an internal explosion. Even it could be a bomb which has been hurled. And there could be an internal explosion leading to generation of fragments of this particle mass m. Say it leads to two particles being generated, one of mass m by 3, the other one of mass 2m by 3. Two particles whose masses are in the ratio 1:2 are generated out of this explosion. at the highest point, let's say, the mass 2m by 3 starts to move vertically upwards, What must be the velocity of the fragment m by 3? What must be the velocity of the fragment m by 3? Okay, now at the highest point, the mass m has only horizontal linear momentum, because u cos 60 degrees is all that it has. It would have shed away all its vertical velocity by the time it reaches the topmost point, right? And at the highest point, it only has a horizontal velocity, which is u cos 60 degrees. So then the only linear momentum at the highest point is along the x direction, that is the I direction. So which is like a m u cos 60 degrees I cap. Mu cos 60 degrees I cap is the only linear momentum that it has. Now, this then gets delegated between these two masses. 2m by 3. Let's say has a velocity v1 in the upward direction, and the mass m by 3, let's say, has a velocity v2 I cap plus v3 j cap. v2 I cap plus v3 j cap is the velocity of the other particle, right? The x and the y direction. Needless to say that if these two vectors are equal, their x and y components must be equal, right? So the x component on the left hand side is like a mu by 2, and the x component on the right hand side is m by 3 v2 I cap v2, m by 3 v2 is the x component on the right hand side. So v2 is known to me. Yes or no? Now, as far as v1 and v3 are concerned, what one could do is, in the j direction, left hand side is 0. So right hand side should be 0 on the j direction. So the right hand side in the j direction is 2m by 3 v1 plus m by 3 v3. That must be 0. So if one of the two, v1 or v3, is known, the other one could be computed. If between v1 and v3, one of them is known, the other one could be computed by applying the law of conservation of linear momentum. Now, well, what I have done is, in principle, I said the linear momentum in the x direction is the same before and after the explosion, and linear momentum in the y direction, 0 before and 0 after. That's what I said by means of these two statements. Now, in the horizontal direction, agree, there was no horizontal unbalanced net force, right? But in the vertical direction, there was despite the explosion, there was gravitational forces acting on m by 3 and 2 by 3. And you would, to begin with, tempted to believe that in the vertical direction, I cannot preserve linear momentum. I can't say that before the explosion, linear momentum in the vertical direction is 0. So, after the explosion, it's going to be 0. Theoretically, no. But then again, the impulse of gravity is small compared to the explosion. The forces of explosion are much larger compared to the to mg. So the impulse of gravity is small compared to the explosive nature of things that happen here, and therefore in the vertical direction, a good enough approximation here could be to preserve linear momentum. There is no harm doing so, right? Now, take another situation. Let's say there is a trolley on a frictionless surface. Let's say the mass of the trolley is capital M. Mass of the trolley is capital M. And there is a man of mass small m at the edge of the trolley. And the trolley is at rest. Initially, the trolley is at rest. And all of this is frictionless. All of this is frictionless. Let's say the man proposes to jump out of the trolley. The man proposes to jump out of the trolley with a relative velocity with respect to the trolley. A certain relative velocity with respect to the trolley. That means on the trolley, somebody would report a velocity of small m. That's going to be the relative velocity of small m with respect to capital M. Whatever capital M tells you about the velocity of small m would be the relative velocity of small m with respect to capital M. So, let's say if the man jumps out of the trolley, then realize that to begin with, the system of capital M and small m had no net horizontal linear momentum. It was all at rest, right? So then if the man adds linear momentum to the system in the horizontal direction, in the rightward direction, then the trolley would respond by moving in the opposite direction so that the algebraic sum of the linear momenta remains zero after the jump as well. So then you would expect the trolley to move backwards. If the man proposes to jump in the forward direction, the trolley, to preserve linear momentum in the horizontal direction, would move backwards and realize that in the horizontal direction, small m and capital M together have no net external force acting on them. So then it would be pretty legitimate to preserve linear momentum for small m and capital M before and just after the jump, right? No net external force acting on small m plus capital M horizontally, right? So then what transpires is, if the man jumps out of the trolley instantly develops a opposite velocity. Let's say the trolley develops a velocity v. The trolley develops a velocity v, and at the same instant when small m develops a velocity u rel with respect to the trolley, relative velocity with respect to the trolley, the man, that means when he's just out of the trolley, develops a velocity u rel with respect to the relative velocity with respect to the trolley. With respect to the trolley, small m develops a horizontal velocity u rel with respect to the trolley at an instant when the trolley develops a velocity v leftwards with a view to preserve linear momentum horizontal. Clear? Alright. Now, from the ground frame, one thing, this is the velocity of the man horizontally with respect to the trolley. But with respect to a ground observer, if this is the relative velocity of the man horizontally and this is the velocity of the trolley leftwards, then what's the absolute velocity of the man? It's relative velocity plus velocity of the observer, right? So then from the ground observer perspective, the velocity of the man, absolute velocity of the man as seen by the ground. The absolute velocity of the man horizontally is going to be his relative velocity plus the velocity of the observer. Velocity of the observer is v leftwards, that is minus v, therefore minus v, yes or no? Absolute velocity would be relative velocity plus velocity of the observer, algebraically or vectorially as is applicable. So it's going to be u rel, relative velocity plus velocity of the observer, which is minus v, right? That's the velocity of the man horizontally seen from a ground perspective immediately after he proposes to jump out of the trolley. V is the velocity of the trolley leftwards. U rel is the observation made by a trolley observer. The ground observer makes this. So now obviously you want to preserve linear momentum from the perspective of the ground frame. In the ground frame, there was no net linear momentum before collision, before the jump, and therefore just after the jump, the net linear momentum of the man plus trolley, just after the jump, the linear momentum of the man plus the trolley is going to be small m to the velocity of the man as seen by the ground observer, which is like a urel minus v and then minus capital MV. That's the net linear momentum just after the jump, yes or no? I'm choosing everything rightward positive, everything leftward negative, and that's the reason I took this as the net linear momentum just after the jump, and this must be 0 and leading to V equal to M urel by capital M plus small m. That's the velocity of recoil of the trolley. That's the velocity of recoil of the trolley just after the jump. Right? Modify this a little bit then. So far so good, right? So you understand what led us to preserve linear momentum horizontally for the man plus the trolley. No net external force acting in the horizontal direction for the system comprising the man plus the trolley, right? Now what we do is, again we have a trolley plus man. But now the trolley is not at rest. The trolley, let's say, has an initial velocity v1 to the right. Let's say the trolley has an initial velocity v1 to the right. Okay. Now in the rightward direction, what's the total linear momentum before anything else happens? Capital M plus small m into v1 is the net linear momentum horizontally before the man does anything. And that must be equal to the net linear momentum just after the man jumps with a velocity urel with respect to the trolley. So now, once given the relative velocity of the man, we would like to ask the ground observer, hey, given this as the relative velocity, what's the velocity of the man as seen by you, my friend? This guy will tell you that, well, if this is the relative velocity, then the ground observer will say that the velocity of the man as seen by the ground observer is going to be the relative velocity. Now, just after this jump, the velocity of the trolley is going to change, right? To accommodate any proposed change in linear momentum, the velocity of the trolley just after the man jumps is not going to be v1, but is now going to be some v2. It's going to be some v2 just at the instant he begins to jump. The velocity of the trolley would change to maintain the same linear momentum, Now, given this as the velocity of the trolley just after the jump, urel as the relative velocity of man with respect to the trolley, what would be the absolute velocity of the man just after the jump? Relative velocity plus velocity of the observer. What's the velocity of the observer? v2. Right, okay. Now we are ready to execute conservation of linear momentum. Just before the man jumps off, the system was housing this amount of linear momentum. Just after this jump, the man held back this amount of linear momentum, urel plus v2, and leaving the trolley with capital M into v2. Right? And this offers ground to be able to compute v2, the velocity of the trolley just after the jump. Given urel, the velocity of the man as seen by the trolley, and the initial velocity of the man plus the trolley, we are ready to evaluate v2, the velocity of the trolley just after the jump. Right? So that's again law of conservation of linear momentum of the man plus trolley horizontally. Right? Sorry? Why don't you just compute that? Solve for v2 and tell me whether it's going to be less than v1 or not. Yeah. कुछ तो लीनियर मोमेंटम चला गया इसके पास, तो इसके पास कम लीनियर मोमेंटम बचा ना पहले से, because now this guy has an additional linear momentum. In a similar manner, you could have had two Johnnies at the two ends of the trolley and jumping one after the other to eternity. One guy ready to jump, another guy again ready to jump. Let's say practically the same mass for the ease of computation. The trolley had mass m, this joker had small m, this joker had small m. So now, let's say this guy jumps, and then after that, this guy jumps. All right. Again, the total linear momentum, no matter what, will still remain 0 before and after the jumps, right? So then after the first jump, let's say this is the first man, this is the second man. And this guy jumps with a magnitude u rel downwards. So you would then expect, since it had 0 linear momentum to begin with, just before the jump, then just after the jump, just after this guy jumps, this would have developed a velocity, let's say, this man plus this trolley would have developed a leftward velocity v to maintain the same 0 linear momentum horizontally, right? 0 equal to, okay, now if this develops a velocity v, what would be the absolute velocity of the man? V rel, u rel minus v. That means relative velocity plus velocity of the observer, which is minus v. So, this guy carries with himself u rel minus v, right? And then minus capital M plus small m into v, right? So, leading to the velocity v as mu rel divided by capital M plus 2 times small m. No, he's not yet jumped. I'm saying that guy, we can make both of them jump one after the other or at the same time. But right now, in this I said, this guy jumps and this guy jumps. Although it will not make a difference, because no matter the order in which they jump, the total linear momentum of the system will remain 0 at all times. So that's inconsequential. But then I'm superimposing as if this guy jumped first and then this guy jumped. The system would respond identically no matter what the order in which they jump. So just after the first guy jumps, this is the velocity of the man, this man plus this trolley leftwards, right? So then we know V, this guy goes out of the scene and we have this system. Now this guy says, it's my turn, I'm going to jump with a velocity u rel leftwards. He says, I'm going to jump with a velocity u rel leftwards, alright? So then, if he says, I'm going to jump with a u rel leftwards, even before the jump, what's the total linear momentum leftwards? M plus small m into v leftwards. I'm taking now leftward positive, right? Net linear momentum leftwards is m plus small m into v just before this guy jumps. All right. Now, just after this guy jumps, this velocity changes to, let's say, v1. This velocity changes to v1 just after the other man has commenced jumping, right? So then, the trolley will retain mv1, the trolley will retain mv1. What about the man? Now, the relative velocity is v. So, the absolute velocity of the man would be what? Relative velocity plus the velocity of the trolley, that means u rel plus v1, right? So, then small m into u rel plus v1, that's a redefined equation. Capital V we already know from these considerations, and V1 is ready for computation from yet again another application of linear momentum for the second jump. Got it? Yeah. You want some water? देख वहां होगा क्या पानी? नहीं है वहां. Let me now take you into a variable mass scenario, right? I mean, this discussion would be useful for analysis of rocket propulsion and of those types, right? So, a simple understanding, nothing difficult about it. Once we understand the principle of conservation of linear momentum, then we are actually aptly and adequately equipped to look into the prospect of analyzing a variable mass unit, right? Let's say this was a system and its mass was small m. At a certain instant of time. And let's say it had a velocity v1. This instant of time, it released a small amount of mass dm. With a velocity v2, right? Small amount of mass dm, it released with a velocity v2. Now, no net external forces acting on the system. One thing, since this mass is so small, the mass that is ejaculated is so small that it's not going to significantly alter this v1 in this short interval of time in which this mass is expelled from the system. So whatever be it, the mass dm was originally present in this, and when it was part of this, when it was integral with this, it had a velocity v1 to the right. Now when it got expelled from the unit, it had a velocity v2. That means for this mass element dm, what has changed? Its linear momentum. For this small unit dm, its linear momentum has changed, right? What's the change in linear momentum? dp. dp is the change in linear momentum. That's going to be dm into v2, final linear momentum, minus dm into v1, initial linear momentum, right? That's a change in linear momentum. Now, let's say this happened in a short time dt. This change in linear momentum on this mass element happened in a short time dt, right? If we are just focusing on this dm, this change in linear momentum happened on this mass element dm in a small amount of time dt, right? That means the rate of change of linear momentum executed on this mass m was dp by dt. Yes or no? That was the rate of change of linear momentum associated with this mass element dm. Okay. Now, rate of change of linear momentum acting on the mass element must be from Newton's second law. The external forces acting on, net of all external forces acting on that mass element, yes or no? That means the force acting on this mass element must have been, this must have been the force acting on the mass element. Who exerted this force? Well, this system of which dm was originally a part, this system, to expel this mass out of it, executed or applied a force F so that its velocity could change from v1 to v2 and the expulsion could take place commensurate. No? Right? So, the main system exerted on dm this amount of force for expulsion of this mass with a velocity v2. Right? Are you there with me on this? Which means, if this is the force that the system exerted on the expelled masses, then from Newton's third law, the expelled mass must have exerted an equal and opposite force on the system, right? That means, see, the system, to give it a velocity v2, exerted a force F on the expelled mass in this direction. The expelled mass will exert on the system a force in this direction equal in magnitude to F, but oppositely directed. So, one thing, this v2 minus v1 is what? The relative velocity of expulsion with respect to the system. This is the velocity of expulsion. This is the velocity of the system. v2 minus v1 would be the relative velocity of dm with respect to the system. v2 minus v1, velocity of dm minus velocity of m is going to be the relative velocity, of expulsion with respect to the system. This dm dt is looked upon as some mu. Kilograms per second. These many kilograms per second is being expelled out of the system. With a relative velocity vrel. v2 minus v1 is the relative velocity of expulsion with respect to the system. Yes or no? Now, the magnitude of the force F, that's going to be the magnitude of the thrust acting on the system. That's going to be the magnitude of the thrust acting on the system also, right? That's going to be magnitude of dm dt into vrel magnitude of dm dt into vrel. Now, dm dt is what? Rate at which mass of the system is changing, isn't it? dm dt is what? The rate at which the mass of the system is changing. That's what is meant by dm dt. That many kilograms per second, rate at which the mass is being. Now, this could be a constant or this could be a variable. These many kilograms per system, per second. These many kilograms per second. Either mass could be actually expelled from a system or mass could also be entering a system. Why not? Right? If mass is being expelled from the system, then the mass is increasing with time. If mass is being expelled from a system, then mass is decreasing with time. This mass is decreasing with time, right? If mass is decreasing with time, then go back to my last class on Saturday. dm/dt should be, if n is a decreasing function of time, dm/dt should be negative, isn't it? If m decreases with time, if m is a decreasing function of time, dm/dt is negative. Did I not discuss monotonicity in the last class? Increasing, decreasing function, that was my whole objective on Saturday. M is decreasing with time, dm/dt has to be negative, right? So, if m decreases with time, then dm/dt is negative. And when does that happen? When mass is being thrown out of the system, expelled from the system, dm/dt is negative. If mass enters a system, then mass is increasing with time, you know. I mean, there could be grains falling from a hopper onto a trolley. Then the mass of the trolley is increasing, isn't it? So mass could also be increasing in a variable mass system. So if mass increases with time, then dm/dt for that system must be positive. Mass increases with time, dm/dt must be positive. Important thing here is, this mu or its magnitude I would use as the rate at which mass is being accumulated by the system or the rate at which it's being expelled by the system, right? Magnitude of the force is magnitude of mu into vrel, magnitude of mu into vrel. In this case, for this situation, for example, what's the direction of the force F acting on dm, right or left? Right. In this case, it's right. On dm, it's right. On dm, it's right. On dm, the force acting is rightwards, yes or no? Huh? What about the force acting on this mass m? Leftwards, right? The direction of the relative velocity of dm is rightwards. Direction of the relative velocity of dm is rightwards, right? dm, the relative velocity of expulsion is rightwards. Force acting on the system is leftwards when the mass of the system is decreasing. That is when dm/dt is negative. It's negative. Write down. If a variable mass system expels mass away, then the force acting on that system, is exactly opposite of the relative velocity of the expelled mass. Similarly, one can establish, write down, that if a variable mass system accumulates mass. That is when dmdt is greater than 0. That is when dmdt is greater than 0. That is when dmdt is greater than 0. The thrust acting on the system, has the same direction, thrust acting on the system has the same direction as the relative velocity, of the mass inducted into the system. I'll quickly summarize this fact for you. One thing, the magnitude of the thrust acting on a system will always be, that is magnitude of the thrust, or rather Ft, which is the magnitude of the thrust acting on a variable mass unit, will be magnitude of dmdt into Vrel. Vrel is magnitude of the relative velocity. This is magnitude of the relative velocity. The magnitude of the thrust acting on a variable mass system would be dmdt, which is that mu. See, why I put a mod around this? Because dmdt could be positive as well as negative. To ward off the minus sign, these two parallel bars are superimposed so that the output of this is always non-negative, right? Is always non-negative. So then, and this is the magnitude of the relative velocity, whether it's expelled or it's being inducted, right? So then, the magnitude of the thrust acting will always be this. And the direction, as far as the direction is concerned, you just need to remember what I made you write. If it's a variable mass system with an increasing mass, then the direction of this thrust, will be the same as the direction of the relative velocity. In a variable mass system with an increasing mass, the direction of the thrust acting on the system, would be the same as the direction of the relative velocity of the mass that is being inducted into the system. Again, for a system with a decreasing mass, the direction of the thrust acting on the system, would be opposite to the relative velocity of the mass that is being thrown away from the system. So, this is how you determine the magnitude, and then based on whether dmdt is positive or dmdt is negative, the direction of this thrust would either be synonymous with the direction of the relative velocity of the mass being expelled or inducted. This is the key thing. So, both magnitude and direction will be in place with the help of these two notions. The magnitude of the thrust, the direction, like I said, based on whether it's an increasing mass or a decreasing mass, it's either going to be synonymous with the direction of the relative velocity or would be opposite to the direction of the relative velocity of the mass being inducted or expelled. Clear? Now, Let's quick illustrate this full manner. There is a trolley at time t equal to 0. It starts from rest. At time t equal to 0, it starts from rest and is being acted upon by a constant external force F. And is being acted upon by a constant external force F. Rightwards, right? There is a hopper, let's say, containing sand. There is a hopper containing sand, a stationary hopper. I mean, you could make this large enough, otherwise you'll get cynical to tell me, hey, it will go out of view. Stationary hopper releasing sand vertically onto this trolley. The sand then collects here on the trolley. The trolley at time t equal to 0, let's say, had a mass m0. And then it was gathering mass because of the sand accumulating in it. It was a system where dmdt was positive, right? And let's say the rate at which this mass is being ejected out of the hopper is, say, mu kilograms per second, is like mu kilograms per second, right? In t seconds, how much of sand would have accumulated here? Mu into t? Let's say mu is constant. Let's say mu is constant, right? So the amount of sand, kilograms of sand that would have accumulated in the hopper would be mu into t. So then, there would be a heap collected at an instant of time t, at an instant of time t. And this would have gathered a velocity because it was being pre-acted upon by force F by this time. Trolley would have gathered a certain velocity v to the right, right? At this instant of time t, the trolley had a velocity v to the right. And the trolley at this instant, that is at time t, the trolley had a mass at this instant which was its original mass, dead mass m0, which it had, plus the additional mass of the sand that it collected, mu t. These many kilograms, this was the instantaneous mass. This was the instantaneous mass of the trolley and its contents. Okay. Mu is therefore like magnitude of dmdt. Mu is the rate at which mass is accumulating. That is dmdt, or its magnitude, right? dmdt here is positive. Why? Because mass is increasing with time. So dmdt is positive. So can I not say that mu is like the dmdt? Because dmdt is positive, mu kilograms per second will match with dmdt. That force F. No, this force is an external force. It has nothing to do with the variable mass system. This is just an external force. Now, in addition to this force, because of the variable mass, there would be a force of thrust acting on this. There would be a thrust acting on the system. Let me explain. Let's see. Okay, now the thrust acting in the downward direction is inconsequential because there is a reaction from the ground which takes care of it, right? So all that is important is the relative velocity of sand with respect to the trolley horizontal, which will be instrumental in producing the horizontal thrust, right? The vertical thrust is not important here because the vertical thrust is not going to produce kinematic changes on the trolley horizontally. It's going to be in fact balanced by an additional reaction from the ground, not matter, right? What's important is the horizontal thrust, which would be a baby of the horizontal relative velocity of the falling mass element, right? Okay. Now, look, this instant of time, please feel free to inquire more, but then, make sure you've understood it very transparently. The trolley had a velocity v to the right, right? The falling mass element had zero velocity horizontally because it was falling vertically. Its velocity horizontally was zero. So a person on the trolley, if you ask that person, what's the horizontal velocity of the falling sand? He'll say v leftwards. No? A person on the trolley will report a leftward velocity v, horizontal relative velocity v of the falling sand. No. Huh? So the direction of the relative velocity of the sand with respect to the trolley horizontally is leftwards. It's a system of increasing mass or decreasing mass? Increasing mass. In an increasing mass, the direction of the relative velocity will be the same as the direction of the thrust acting on the system. So if the direction of the if the direction of the relative velocity horizontally of this falling mass is leftwards, the additional thrust acting on the trolley would be leftwards. Why? Because it's a system of increasing mass. It's a system of increasing mass. I hope I have not confused you. Then let me try more. Right? So then the thrust acting on the trolley is leftwards because the system is of increasing mass and the relative velocity horizontally of sand with respect to the trolley is leftwards. There is a vertical relative velocity also, but then it's not going to participate in our system at all for the computation of the kinematic status of the trolley and its contents. Okay. Once I know the direction of the thrust, I should be now in a position to readily compute the magnitude of the thrust acting on the trolley, right? The magnitude of the thrust acting on the trolley would be the rate at which mass is being accumulated, magnitude of dm dt, which in this case is mu, into the magnitude of the relative velocity, which is v. Magnitude of the relative velocity of sand with respect to the trolley is v horizontally. So this is the magnitude of the thrust. Are you all comfortable with this? Now, so at this instant of time when the trolley has a velocity v to the right, it's being acted upon by a force F, external rightwards. The problem tells you that it's a constant force and a thrust, variable thrust. Why? Because v is changing with time. So this thrust is not a constant force, it's a variable force because v itself is changing with time under the influence of everything that's being factored in, right? The net of all forces acting on the trolley and its contents is F minus Ft. F minus Ft to the right. No? F minus Ft, which is mu into v. That from Newton's second law must be mass into acceleration dv dt. But the mass at this instant is what? M naught plus mu t. M naught is dead mass at t equal to 0. Mu is the rate at which the hopper is releasing sand. these many kilograms per second. And then we have this, F is a constant force. F is a constant force acting, right? And then it takes no rocket science to figure out that dV by F minus mu V is dt by m naught plus mu t. One could integrate both sides. At time t equal to 0, what was V? V was 0. V was 0. At time t equal to t, let's say V became some V. V became some V. Clear? Now, tell me, what would be integral dV by F minus mu V? Can I make, what's the derivative of F minus mu V with respect to V? Minus mu. Minus mu, right? Can I not make the numerator the derivative of the denominator by multiplying by a minus mu? The numerator would then become the derivative of the denominator. And if the numerator is the derivative of the denominator, the integral is logarithm of the denominator. The integral is logarithm of the denominator. So this is like a minus 1 by mu log F minus mu V. Right? That's the left hand side. Similarly, if somebody said, let's say integral dt by m naught plus mu t, hey, I can make the numerator the derivative of the denominator. The integral will become logarithm of the denominator. I've given you this result in the past, right? So this becomes like a 1 by mu log m naught plus mu t. Right? Now what I do is apply the limits. This will give me, see, mu and mu will get cancelled from both sides when you integrate. So we have like a minus 1 by 1 by F minus mu V. V runs from 0 to V is, I'm sorry, logarithm of this minus log F minus mu V. V runs from 0 to V, and the right hand side is ln m naught plus mu t. T runs from 0 to t, right? When you supply the limits, definite integral, clear? So, the value of this at v equal to v minus value of this at v equal to 0. Log f minus mu v minus log f minus 0. But log a minus log b is log of a by b. Right? The right hand side is log, final value is m naught plus mu t minus initial value would be log m naught, so minus log m naught, so by m naught. Right? And this minus can find a place here, to the power minus 1. Can find a place here in the power, right? So then if log of a is log of b, that means a must be equal to b. So you can plug in this equal to this, which is to say that f minus mu v by f equals m naught plus mu t by n, this to the power minus 1, this to the power minus 1. And then you can solve for v as a function of time, right? You can then solve for v as a function of time, the velocity of the trolley in terms of time. Are you okay with it? The important thing is, when I talk of relative velocity, then for a mass that is entering the system, just before it enters, for a mass that is leaving a system, just after it leaves, that's a relative velocity. That relative velocity, just before it enters and just after it leaves, that's a relative velocity in contention. Clear? Look at a similar system in which mass is leaking out, mass is being taken away from the system at a certain rate. Let's say at the rate of mu kilograms per second, the system is releasing mass, right? Again, a similar trolley and its contents. At time t equal to 0, let's say it had a lump of sand. So m naught was including the sand, right? M naught was including the sand. And there was an external force F acting at time t equal to 0. Let's say the velocity of the trolley was at rest. M naught was the total mass of the trolley, the dead mass plus its contents, the sand, that is, right? And there was a small orifice produced here. That was discharging sand at the rate of mu kilograms per second, right? Mu kilograms per second. It was discharging sand vertically downwards at the rate of mu kilograms per second. Now, t seconds later, the trolley and its existing contents would have developed a certain velocity, right? Let's say at an instant of time t, the trolley and its contents develop a velocity v. The mass then would be mu t kilograms less, So mass at this instant of time t would be like a m naught minus mu t. This would be m as a function of time, m naught minus mu t. It's a system of decreasing mass. Now in this case, dm dt is negative. Mu is a positive number. It tells you these many kilograms per second being expelled, right? Mu is positive always. Whether it's entering or leaving, mu is positive, but dm dt comes married to a sign, positive or negative, right? So then, very clearly, if dm dt is negative, dm dt cannot represent mu. But if I multiply dm dt with a minus sign, then dm dt would become positive. Or in other words, mu is actually magnitude of dm dt. Right? these many kilograms per second expelled. But dmdt is, hey, mod A is minus A when A is negative, yes or no? Mod A is minus A when A is negative. In this case, dmdt is negative. So mod of dmdt would be minus dmdt because dmdt is negative. And why is dmdt negative? Because m is a decreasing function of time. M is a decreasing function of time. कंफ्यूज है क्या भाई? नहीं, और थोड़ा ट्राई करता हूं फिर. Got me? Now answer this. Obviously, relative velocity of the sand just after it emerges from the orifice in the horizontal direction would be the one that would be counted towards computation of the horizontal thrust. Relative horizontal velocity of the expelled sand from the orifice horizontally just after it emerges from the orifice, that would be the one that will be used towards calculation of the thrust acting on the trolley and the remainder of the contents. Yes or no? Now answer this question of mine. Let's say at a certain instant when the velocity of the trolley is v. That instant, there would be mass that is being expelled from this orifice. That instant, what would be the horizontal velocity of the expelled mass? What would be the absolute horizontal velocity of the expelled mass? It's going to be v only rightwards. Inertia. See, just after it released, when it was in contact with the trolley, it had a velocity v to the right. So for this scenario, when it's just being expelled, see, it's not like you are heaping it. You are allowing it to fall naturally down the ground. So then, do you realize that this mass has inertia in this case? In this case, it may not always be the case. In this case, it has inertia. So the velocity of the falling mass at an instant when it's just about to exit will be the same as the velocity of the trolley. So then what's the relative velocity of the expelled mass in this case? 0. The relative velocity of the expelled mass is 0. If the relative, horizontally, if the relative velocity of the expelled mass is 0, what's the thrust that it exerts on the trolley? 0. Mu times relative velocity, 0, right? So no thrust acting in this case, no thrust acting on this in this case on the trolley despite the release of sand through the orifice because of inertia considerations in this case. In this case, inertia considerations, right? There is no external, there is no mechanism or motor or something which is releasing the sand at a rate different from v. Got me? So then, thrust acting is 0. Thrust acting is 0. So the only force acting is F. The only force acting at this instant is F. And on what mass? On m0 minus mu t. V is the velocity. So then from Newton's second law considerations, F then is m0 minus mu t mass at this instant into dv dt. No thrust acting, just this F acting. This is the simple model of this system in this case, right? No? And then again, no rocket science once again to be able to compute v as a function of time, because dV then is like a F by m naught minus mu t dt. Right? Separate variables. Integrate both sides. At time t equal to 0, what was V? 0. In this case, V was 0 at time t equal to 0. It starts from rest. At an instant of time t, what is V? Some V. Right? The left hand side, when you integrate and supply limits, it will be V minus 0 V. The right hand side is going to be minus 1 by mu. Again, you can make numerator the derivative of the denominator. Minus 1 by mu log m naught minus mu t. T runs from 0 to t. Right? Which is minus f by mu log m naught minus mu t by m naught. That's V. That will be V as a function of time. That will be V as a function of, in fact, thrust means in the vertical direction. उसको लात मारेगा ना तो भी कुछ नहीं होगा, सीधा लात मारेगा, ठीक है? Because in the horizontal direction it will still have zero relative velocity. You know what I'm saying? Relative velocity in the horizontal direction, if you are not altering that, it will appear to fall vertically. For a person inside the trolley, the sand at that instant will appear to fall vertically downwards. It will not appear to move horizontally. I mean, it's like this, my friend. From outside the window of a train, put your hand out and you release a ball. At that instant, do you realize that the ball will share a common velocity horizontally with you? So in the horizontal direction, there would be no relative motion. So it will appear to fall vertically at that instant. A common horizontal velocity. Got me? Same concept here. Hai na? Oh, who will force that? Yeah, then that's another issue. If you're forcing it by a motor, that means then you are imparting it a different horizontal velocity. Then you look at what the motor is doing. Then somebody would have to tell you what the motor is doing. Now, which is what I'm going to tell you now when I come to some rocket science. Let's come to rocket science, though it's no rocket science either. But we'll talk a little bit about rockets where, another case of expelled mass, but internal combustion will register a different velocity for the expelled masses compared to the rocket. Right? It will release fuel at mu kilograms per second at a velocity different from the velocity of the rocket. Now that's the system that I'm going to. But then that would have to be done by some combustion process or something else would have to do. But on its own, it will be benign. So let's say this was a rocket. Okay. Obviously, now there would be an additional force mg acting on the rocket. The mass of the rocket would vary, so mg would be different at different times. So that's like an variable external. In the earlier case, that F was constant. right? But in this case, the F, because of gravity, would be different because the rocket is going to expel masses away, and therefore the mg acting on the rocket would be different at different instance of time, right? Now, let's say at time t equal to 0, the rocket was given an initial impetus, was given an initial upward velocity u, right? Not at time t equal to 0, the rocket was given an upward velocity u. And then a certain mechanism inside the rocket, a combustion mechanism inside the rocket, or some other sophisticated mechanism inside the rocket is releasing mass out of the rocket at a rate mu kilograms per second. At the rate mu kilograms per second, the rocket had an initial mass m equal to m naught. At an instant of time t, let's say the rocket developed a velocity v because it expelled a mass downwards, so it imparted momentum to this mass downwards, so it exerted a force downwards on the expelled mass. The expelled mass will therefore push it upwards. So it would therefore progressively develop more and more velocity. So some instant of time, the rocket develops a velocity. Okay. Now, at this instant of time, let's say the mass was m. And in this case, is dm dt positive or negative? Dm dt is negative. Why? Because m is decreasing with time. The rocket is becoming lighter. Dm dt is negative, right? In this case, so minus dm dt would be positive. Minus dm dt would be positive. Dm dt is negative. Minus dm dt would be like our mu kilograms per second. That's going to be, right? This is the rate at which mass is being expelled. And let's say it's being expelled by some mechanism with a constant relative velocity. That means even though the velocity of the rocket is changing with time, the velocity of the expelled masses will also change with time, but in a manner that the rocket observer will always report the same velocity of the expelled masses. That means the relative velocity of the expelled masses, let's say, is remaining constant. Relative velocity of the expelled masses will remain constant. Such is the mechanism. So, at this instant of time, the magnitude of the relative velocity of the expelled masses would be vrel downward. Hey, did I tell you that in a decreasing mass system, the thrust acting on the system is going to be opposite to the direction of the relative velocity. So, if the direction of the relative velocity of the expelled gases is vrel downwards, then the rocket will experience a thrust. The magnitude of the thrust experienced by the rocket upwards. Is going to be minus dm dt into vrel. Why? Because dm dt is negative. I have to make it positive because I am looking at the magnitude of the upward thrust. So minus dm dt into vrel. Vrel is a number. The magnitude of the downward relative velocity of the exhaust gases, right? So then Ft, I am saying, is the magnitude of the upward thrust, so it must be positive, right? But dm dt is negative, so I multiply it with a minus sign so as to make it positive to get the magnitude of the upward thrust. Got me? will of the exhaust gases we are proposing to change it in a manner, the internal mechanism would do such things to the exhaust gases such that the relative velocity is remaining constant. So obviously the absolute velocity of the exhaust gases will also change with time. But I am proposing to maintain constant relative velocity of exhaust. This will change. The absolute velocity of the exhaust will also change, but we want to maintain the same relative velocity of the exhaust. ठीक है ना? So then, that's the magnitude of the thrust minus dm dt into magnitude of the relative velocity vrel downwards. What is the summary of all forces acting on the system at this instant of time? The upward thrust, vrel minus mg downwards. At this instant, there is Mother Earth acting downwards. And this must be equal to mass into dv dt. Mass into dv dt from second law. Sorry? No, but can't I maintain it like this if I want to? Maybe towards the end I'll put m equal to m naught minus mu t. But otherwise I'm simply saying m is a function of time. Who stops me from doing that? Right? I can take a call on that towards the very end of my algebra, right? But until then, I might just want to maintain neatness in my algebra. Therefore, I would rather leave it in this format. All right. So then, we propose solving for V as a function of time. VREL is part of the larger specifications of the rocket. The internal mechanism is doing VREL, right? Now, it will be a little utopian to imagine that for a rocket, which is, you're not talking of Diwali ka rocket, which goes like a few hundred meters or so, but we're talking of an actual rocket, in which case G is not constant. G is not constant, isn't it? But then let's say we still talk of, for a simple scenario, we talk of a uniform G. Otherwise, I can put G as a function of height, right? But then to make life simple, at least to begin with, let's imagine G to be constant, right? Although, it's going to travel several radius of the Earth, so n times 5,600 kilometers or more, which would deprive it from a constant G kind of scenario. But again, the physics is more important. That will be part of the algebra if we wanted to. But then let's quickly look at the simple dynamics of rocket. Let me divide by m. M is not a constant here. M for sure is a variable. So let me divide by m. So I get like a minus dm by m. VREL, I'm sorry, dm by m. VREL minus g dt equals dv. Right? Let me integrate both sides. M was originally m naught, and at some instant of time t it became m. Right? M runs from m naught to m at some instant of time t. T goes from 0 to the instant of time t when m became m, and V goes from initial velocity u, the initial velocity. You have to propel the rocket with a certain velocity u, right? Velocity u, and at some instant of time the velocity became v. Simple, because then this would become like VREL is a constant, can come out. So minus VREL. And Gm by m is going to be log m. So it's going to become log m minus log m naught, which is log m by m naught. Minus gt equals v minus u. G comes out, assuming constant, equals v minus u. V then would become u plus this. What's the confusion? Minus v. Huh? Oh, I'm sorry. Oh, I'm so sorry. I realize, all of you were casting very dirty glances. So I couldn't figure out. That was a typo though. So log m by m naught is minus gt, v minus u, etc. V then would become u minus gt minus vrel log m by m naught, etc. Now, generally what happens is that the forces of the thrust created by the expelled masses is much larger. Thrust created by the expelled masses is much larger than what Mother Earth mg is doing to the system, right? And again, the Mother Earth is acting less and less. Why? Because number one, g is decreasing as you move up. Two, the mass is also decreasing. So mg is really decreasing because m is also decreasing. So the rocket is becoming lighter, g is decreasing. So then, what we could sometimes do is, we could ignore this as another level of approximation. We could ignore the force due to gravity mg because it's smaller than the force because of the thrust. This is the force because of the thrust. So if this is, let's say, some 10 to power 20 and this is like 0.01, then you might as well ignore this, isn't it? If it's in that ratio, you can. So for another level of approximation, you could ignore this. Then the variation of g with height and therefore with time becomes irrelevant for analysis. And then you get even a simpler variation. So if somebody says ignore gravitation, then you write this equation and cover this term up and move on. And that will be again easier to integrate. That will be dm by m into vrel is dv dt to cut jayega. So you can compute velocity as a function of mass in a given instant. And towards the end, you can put m equal to m naught minus mu t if you so want. But, so that was snippet of rocket science, right? Again, nothing difficult about it. It's a simple application of the variable mass scenario. Obviously, the actual rocket model is a lot more complicated than this. It's not difficult, but there are more number of terms, and then there is heat transfer involved, there is mass transfer, heavy amount of equations, both mechanical and otherwise involved in the whole game. But then you keep adding more and more. It's like when you're a small kid, they don't talk of essays. They start you with alphabets, then they teach you words, and then they teach you sentences, and then they teach you small paragraphs, and then essays and stories, and so on and so forth. And then you start reading books. But then, as a small kid, if you were said, "Paida hote hi usko bolo, go and read Agatha Christie," that's not going. So again, it's not difficult. But then when you grow in stages, as you keep learning more and more things, it's not going to be difficult. But then a beginner level understanding of rocket propulsion of this kind will do the trick for you for the time being. If you've understood things that I've said to you so far, then this far and no further on variable mass systems. Got me? Now, let's say you have a collection of two particles. You have a collection of two particles M1 and M2. And let's say there is a certain force F1 acting on M1, and there is a certain force F2 acting on M2. And M1 and M2 also interact with each other. There are mutual forces of interaction between M1 and M2, such as the unit M1 and M2, right? Let's say M2 exerts on M1 a force F1, and consequence of third law, M2 will exert on M1 an equal and opposite force F. That means F1 would be minus F2. F1 would be minus F2 vectorially, consequence of third law. Alright. At some instant of time, let's say the position of M1 was R1, position of M2 was R2. Now, look at M1 alone. What's the net force acting on M1? The vector sum of F1 and small f1? That must be mass into acceleration of M1, mass into acceleration of M1, right? Yes or no? Let me apply Newton's second law to M2. This is all that is acting on M2. The external F, and the force that M1 exerts on M2 is F2, small f2, and that must be mass of M2 into acceleration A2 into acceleration A2. Now, this was looking at M1 and M2 in isolation. Let me take a consolidated look on M1 and M2. That means if I regard M1 and M2 as one single system, one unit, then capital F1 and capital F2 are external forces acting on the system, and small f1 and small f2 are pair of internal forces acting on the system, right? Pair of internal forces acting on the system. Let me add these two. F1 plus F2 plus F1 plus F2 is M1A1 plus M2A2. Hey, but F1 plus F2, small f1 plus small f2 is 0, right? For the system, the internal forces will constitute action-reaction forces, and they would cancel off in pair, right? So then, and F1 plus F2 is the net external forces acting on the combo. Net external force acting on the combo is F1 plus F2, capital F1 plus capital F2. F net external. So F net external plus F1 plus F2 is like M1 A1 plus M2 A2, because this plus this are up to nothing. Now what one could conceive is the following. For the system comprising M1 and M2, the unbalanced force is this. The others were part and parcel of the internal action reaction, cancelling off conveniently. What one could really imagine is this F net external. See, this is a notional idea. It's a notional idea, right? What one could imagine is, instead of M1 and M2 as two discrete masses placed at locations R1 and R2, imagine one single mass, M1 and M2, M1 plus M2, imagine one single point mass, M1 plus M2, having an acceleration A. This F net external is doing like a M1 A1 plus M2 A2. This, if you recall, when I was doing Newton's second law, I told you this is generalized Newton's second law. This I told you was generalized Newton's second law, right? So in any case, now what I do is, this is like M1 plus M2 into the acceleration of that particle. Then I am notionally imagining, right? Now I imagine a particle notionally having a mass M1 plus M2, having an acceleration A, produced out of a net external force, this capital F1 plus capital F2. So then this particle, which is replaced by the combination M1 plus M1 and M2, this particle having a consolidated mass, lumped mass M1 plus M2, is replacing the combo of discrete particles M1 and M2 by another point particle located not at R1 or R2, but located, let's say, at some R, located at some position R. Then this notional position, and this notional mass M1 plus M2, this notional position R, where this mass is said to be located, and this notional mass M1 plus M2 is said to be the sort of mass of this combination. This position where M1 plus M2 is notionally said to be located, and when acted upon by a force, this produces an acceleration, this is said to be the center of mass of this combination, and its acceleration is written as ACM, the acceleration of the center of mass. It's said to be the acceleration of the center of mass. Are you there with me on this? So then, if I have two particles M1 and M2 have acted upon by a certain force, and the accelerations of M1 and M2 are A1 and A2, then this combination could be replaced by one point particle of mass M1 plus M2 having an acceleration ACM. This notional position would be referred to as the center of mass position or the center of mass particle of the collection M1 and M2. So, this ACM this is the acceleration of what we refer to as the acceleration of the center of mass. That means this collection could be replaced by one single particle having mass m1 plus m2 and having an acceleration ACM. Right? And then what I could do is realize that A1 is d2r1 dt2, right? That's A1, isn't it? A1 is d2r1 dt2, A2 is d2r2 dt2, and if the center of mass position, that means this notional position m1 and m2 replaced by one single particle of mass m1 plus m2, and when this notional particle is being acted upon by a force F1 plus F2 is being acted upon by a force F1 plus F2, which is like a F net external, it produces on M1 plus M2 an acceleration ACM. This position is the center of mass position between M1 and M2, and if M1 is located at R1, M2 is located at R2, and then this center of mass position, let's say at this instant, is located at some R, then what would be the acceleration of the center of mass? d2r dt2, that's going to be the acceleration of this particle. The second derivative of r with respect to time, that's going to be the acceleration vector associated with this notional particle, right? So then ACM is going to be d2r dt2. Yes or no? Can I just remove the clutter from here? Now what I do is this ACM I write as d2r dt2, that's m1 d2r1 dt2 plus yes or no? Can I not rewrite this as d2r dt2 as second derivative m1 r1 plus m2 r2 could equivalently do this? Yes or no? Which means, what is this R? This R is the position of that notional particle, the center of mass particle. R1 is the position vector of the mass M1, R2 is the position vector of the mass M2 at a certain instant of time. Both R1 and R2 will vary with time. So the position vector of R in the center of mass will also in general vary with time. This R is referred to as the position vector of the center of mass of this collection of this pair M1 and M2. I could then say that, well, R could be looked upon as the position vector of the center of mass, which is M1 R1 plus M2 R2 by M1 plus M2, right? So there are two particles, mass M1 and M2, located at positions R1 and R2. Then the two particles for the sake of applying Newton's second law, could be replaced by one single particle having mass m1 plus m2 located at RCM equal to m1 r1 plus m2 r2 by m1 plus. That's the center of mass position for a collection of two particles. It could just be conveniently extended to any number of particles. So this single particle is what? Is a representative particle for that collection. If you want to apply Newton's second law, instead of applying Newton's second law to each particle separately of this collection, you could apply it to the representative particle, the center of mass particle located at m1 r1 plus m2 r2 by m1 plus, right? And the mass of this notional particle is m1 plus m2. And if there are n number of discrete particles, then we could simply write the position vector of the center of mass of these discrete particles if I had, let's say, m1 located at r1, m2 located at r2, similarly mn located at position vector rn, then the position vector of the center of mass is going to be given by summation mi ri, I equal to 1 to n, that is m1 r1 plus m2 r2 divided by summation mi over all the particles. This summation is carried out over the entire collection of discrete. That's the center of mass, position vector of the representative particle. If one wants to apply Newton's second law to refute this. Got me? In fact, the velocity of the center of mass, if I differentiate this with respect to time, I get the velocity of the center of mass particle, the notional particle. The velocity of the center of mass particle then is going to be summation of mi. If I differentiate ri with respect to time, I get the velocity of the ith particle vi, right? It's going to be summation mi vi by summation mi. That's going to be the velocity of the center of mass particle. In fact, the total linear momentum of this collection is going to be represented by the linear momentum of the center of mass. The total linear momentum of this collection, summation pi. So summation pi, that's going to be the linear momentum of the center of mass particle, which would be VCM into summation mi. The center of mass particle has mass summation mi, right? It's going to be summation mi total mass into VCM so instead of computing the linear momenta of individual particles, if you want to know the total linear momentum of the system, just look at linear momentum of the center of mass. Just look at linear momentum of the center of mass. In general, a single vector equation would reduce to three scalar equations. In the sense, position vector of the center of mass is like summation mi ri by summation mi, where the position vector of the ith particle is going to be some xi I cap plus yi j cap plus zi k cap. That's going to be the position vector of the ith particle, right? Position vector where I could be like 1, 2 up to n, whereas the position vector of the center of mass is going to be, the center of mass will have an x coordinate right? So XCM I cap plus YCM J cap plus ZCM K cap, right? Now, if you plug in XCM I cap, YCM J cap, ZCM K cap on the left hand side, and all the RIs you replace by XII, YIJ, ZIK, I runs from 1 to n, and equate the I, J and K components on both sides of this vector equation, you're going to get like a XCM as summation MIXI by summation MI, the x coordinate of the center of mass, m1 x1 plus m2 x2 plus m3 x3, etc. by m1 plus m2. Similarly, the y coordinate of the center of mass is going to be summation MIYI by summation MI and MIZI by summation MI. X, Y and Z coordinate of the center of mass could be computed from the X, Y, Z coordinates of the constituent particles of the system. In fact, this was a collection of discrete particles, all particles at different locations. We could have a continuous distribution of particles. We could have had, so that was a discrete collection. We could have had a continuous distribution of particles in a certain region of space. In a certain region of space, we could have had a continuous distribution of particles. What we do here is that in this continuous distribution, we look at a certain mass, small mass element dm, certain mass element dm of this continuous collection, and this mass dm located at r. Now, instead of having summation MIRI, we have dm into r. We can break this entire region into infinite number of dms. Right? We have infinity of these dms constituting this collection, and each dm is located at different r. So for each dm, we do a calculation, dm into the corresponding r plus dm into the corresponding r plus the dm into the corresponding r, and we add all the dm into r's like the summation MIRI. We add the dm's into r's. So addition of dm into r's is like integral dm into r divided by sum of all the dm's. And this integration we carry out for the entire bunch, for the entire continuous region, so as to incorporate every single dm constituting this region. Right? That's what this means. This means, I'll repeat. Dekho, in a discrete collection, what did we have? We had summation MIRI. That means we took a mass element into its position vector, another mass element into its position vector, and we carried out a summation. When I was teaching you integration, definite integrals, recall that I said, now in this case, what is it that we want to do? We want to do exactly the same. In the earlier case, we had the MI is located discretely. Now we have these mass elements located continuously. Every point of this region has a mass element dm. So for every mass element dm, there is a certain position vector that you can associate. You can take a dm here and its position here. So we need to carry out a summation of all the dm into r's. A summation of all the dm into r's is the process of integration. This dm into r, integral dm into r, if this integration is carried out with suitable limits to include every dm constituting this region, then we'll get a summation MIRI for this region or not. Yeah, so I'm not saying r is a constant, I'm not saying r will come out. R is a variable, it will depend on where the dm is located. Yes, of course, r will keep changing, it will be different for different dms. So a summation of mass into r for every mass element present in this continuous region could be carried out, divided by the total mass. Total mass would be sum of all the dm's. Right? Now if this integration is carried out with suitable limits, so as to incorporate every dm constituting this region, then I'll get the position vector of the center of mass of this region, then I'll get the position vector of the center of mass of this region. Yes or no? Right? In fact, in a more general sense, in its scalar version, the x coordinate of the center of mass would be obtained if I took a certain dm into its corresponding x coordinate. Would be like mixi mass into the corresponding x, another mass into the corresponding x, another mass into the corresponding x, and I add all of them by supplying suitable limits to this integral to cover all the mass elements, right? Then this would be like summation mixi kind of a stuff divided by the total mass dm. That will give me the x coordinate of the center of mass of this continuous distribution. Similarly, the y coordinate of the center of mass is going to be given by y dm by and so on. Got me? In fact, you could have had, so for every continuous region also, you can replace that region by a single point, which is the notional center of mass point, on which Newton's second law could be directly applied without looking at the individual particles separately and creating clutter out of it. Right? For discrete and for continuous, a notional position, the center of mass position, could be arrived at with the help of some basic algebra. Clear? You could now, not just that you would always have only continuous or only discrete, you could have a combination of continuous and discrete regions, right? In the sense, it's like, look, all the students here are discretely located, but every single student is a continuous system. You have your center of mass in Howrah, तुम वहां छोड़ के आते हो बाकी सबका center of mass कहीं कहीं है, right? So I can replace this by one single particle at its center of mass. I can replace this by one single particle at Howrah, this by one single particle wherever it is. So it's like several continuous bodies discretely placed, right? This region is a discrete distribution, but every single entity of this region is a continuous distribution. That's how it is, right? So you could have a heterogeneous collection of this kind in a typical system. Continuous systems placed discretely. Continuous systems placed discretely, right? Let's say this is a continuous system of mass m1, and the center of mass of the system is located at some r1. The center of mass of this is located at some r1. Another continuous system of mass m2, and its own center of mass is some r2. Similarly, let's say a mass mn in such units, and the center of mass of this unit is Rn, right? And this entire collection m1, m2, m3, mn can be replaced by one single particle having mass m1 plus m2 plus m3 plus mn at a point RCM. That's a position vector of the center of mass of this entire assembly. Is going to be m1 r1 plus m2 r2 plus mn rn by m1 plus m2 plus mn. So this is a combination of continuous and discrete, and for each of these I can find the corresponding center of mass. These r1, r2, r3 are the center of mass locations for these discretely placed continuous entities. We've got started with center of mass. We'll have to really build it up, because now if I start the next stage on center of mass today, it's going to take me 1 unit of 2.5 hours to stop. So I'll have to stop here instead. Alright. This, most of you knew all this because this was covered in school. But then this was the basic idea. It was a formality for me to at least introduce this to you, just in case there were some lacunae here and there. On Saturday, we then meet at our scheduled time of 4 o'clock and we continue with more of calculus. Right? Please come very well prepared. I do not know why. I thought, you'll be... reason I taught variable mass today was because I thought, by this time, if I say m is increasing with time, dmdt is positive and so on and so forth, you'll be ready with the answers. But I don't know why, but you seem to remain oblivious of what was done in my last math class. I thought, I spelled my heart out talking of monotonicity, increasing, decreasing, and so on and so forth, and you were giving me such cold, blank stares. I was so shocked. Please come prepared with the stuff that I have covered in the class so as to make the next class meaningful. Alright?